Dear students, continuing with our lectures on organic reaction mechanism, this is our 31st lecture in this series and second lecture on nucleophilic aromatic substitution. In the previous lecture, we have discussed about SN-AR mechanism, and in this mechanism we will see that although the product formed in some reactions is same, but the mechanism followed is different, and this different mechanism than SN-AR is called as benzene mechanism, and in this lecture we will discuss about the details of benzene mechanism. As I have told you that nucleophilic aromatic substitution reaction is where a nucleophile displaces a good leaving group, and in most of the nucleophilic aromatic substitution reactions the leaving group is a halogen, and the second condition which is must for aromatic substitution is the presence of an aromatic ring. So any aromatic ring where a nucleophile displaces a good leaving group, that is called as nucleophilic aromatic substitution reactions. And as I have told you in the previous lecture that nucleophilic aromatic substitution may take place by different mechanisms, and the main four important mechanisms involving nucleophilic aromatic substitutions, they are SN-AR mechanism, which we have discussed in our previous lecture, that is lecture 30th during organic reaction mechanism series. And today we will discuss what is benzene mechanism. So whenever the aromatic systems they are reacted in presence of very strong bases, and proceed through arine types of intermediate, that type of mechanism is called as benzene mechanism. And similarly, if reactions they are initiated by electron donors, then those types of reactions they are called as SRN1 mechanism, and the reactions involving aromatic system with diazonium salts is called as SN1 mechanism. And these two mechanisms we will discuss in the next lecture, and in this lecture we will be discussing mainly benzene mechanism. And this is the general reaction for aromatic nucleophilic substitution, which you already know. In the previous lecture I have told you that aromatic system having a good leaving group, when it is attacked by a nucleophile, the nucleophile replaces the leaving group, and we will get these types of product, and the reaction is known as nucleophilic aromatic substitution reaction. Now the benzene mechanism elimination mechanism for nucleophilic aromatic substitution was established in 1902 by isolating Messenheimer salts as the key intermediates. And in the first half of the 20th centuries, it was noticed that there are some nucleophilic aromatic substitution reaction which proceed through a different mechanism, and there the mechanism is opposite to what we have seen in case of SN-AR mechanism. There the first step was addition, then elimination, whereas these new mechanism oriented substitution reactions, they first undergo elimination and then addition of the nucleophile take place. So this is a different mechanism than SN-AR mechanism. and this elimination addition mechanism mainly involves benzynes as the intermediate. For example, when chlorobenzene was treated with a strong base like either potassium amide or sodium amide in liquid ammonia, and we know the temperature is minus 30 to minus 33 degrees centigrade, and when this chlorobenzene was reacted under these conditions, it gets converted into formation of aminobenzene or aniline. And you can see over here that the reaction is taking place at a very low temperature, whereas if this reaction follows SN-AR mechanism, then we require very high temperature. And second observation in these types of reactions was that if the ortho position to the leaving group, that is halogen, they are blocked or they are substituted by some other group, say in this case we substitute these hydrogens as methyls, then no reaction take place under these conditions. So that means the mechanism being followed in these types of transformation reactions involving a strong base at low temperature is not the addition elimination mechanism, but it is a different type of mechanism. So that means if the reaction is to take place by this mechanism, then presence of hydrogen is must at the ortho position to the leaving group. So then another observation was done that if only one ortho position is substituted by some other group, say in this case if this is substituted by methyl group, but here we are having the hydrogen, then two products they were formed, ortho and meta products they were formed, but no para product was formed. So this was another observation which led to the conclusion that there is an involvement of another mechanism other than addition elimination mechanism. So the existence of this other mechanism was explained in 1953 by Roberts. So when he established that there is an involvement of a short-lived intermediate bearing a carbon-carbon triple bond which is called as benzyne. So he established that when chlorobenzene is reacted under these conditions, there is a formation of this type of intermediate which is a symmetrical intermediate. Benzyne is present, and he established this through use of isotopic labeling experiments. What he did is he took chlorobenzene where this carbon to which the halogen is attached is a C14 carbon. So when this was reacted under these conditions of strong base in liquid ammonia, then two types of products were formed. That 50% of the product was formed where the nucleophile got attached to the carbon which is C14 carbon or carbon at which the leaving group was attached, and 50% of the product was formed where the nucleophile gets attached to the carbon adjacent to the C14 carbon. Adjacent to the C14 carbon means adjacent to the carbon to which the leaving group was attached. So that means there is a formation of two products in equal yield, that is 50% of each, and two products of equal yield can only be obtained if there is a formation of a symmetrical intermediate which can be attacked by the nucleophile at both the carbons with equal ease. So that is the reason he said that this type of symmetrical intermediate is involved in such type of reactions. because here if you attack at this carbon or this carbon, you will get 50% of the product formed in these cases. Now when the triple bond of benzene was studied, it was found that this is not a true triple bond as is present in alkynes, because in case of alkynes there is an overlap between two 2p orbitals, whereas in case of this benzene the triple bond is formed through overlap of two adjacent sp2 hybrid orbitals. So these adjacent hybrid or sp2 hybrid orbitals, they overlap to form a triple bond in case of benzenes. So and this is at right angle to the aromatic pi system. So pi system is present in one plane and these are present at right angle to the plane of the pi orbitals present in the aromatic ring. And this strain energy for benzene is about 50 kilocalories per mole. So that means the benzene molecule is very much strained molecule, that is why this is a very short lived intermediate, and this is more strained than the cyclopropane by which is having a strain of 28 kilocalories per mole, whereas this is having 50 kilocalories per mole, and this is slightly less strained than cyclopropene ring, which is having a strain energy of 54 kilocalories per mole. And if we see the resonating structures of this benzene, we can see that these sp2 hybrid orbitals, both the electrons, they can be present in this orbital, then this will be having negative charge, and this will be having positive charge. This red mark is for say C14 carbon, whereas if both the electrons they are present in on the C14 carbon, then this will be having a negative charge. So that means the nucleophile, that is NH2, can attack the electrophilic carbon. So 50% chances that this resonating structure may be involved, and 50% chances is that this resonating structure may be involved in the attack of the nucleophile. If the nucleophile attacks this carbon, then NH2 will get attached to this carbon, that is adjacent to the carbon where halogen was attached, and if the NH2 negative imide ion attacks this carbon, because this is electrophilic, then we will have 50% of the product where the NH2 is attached to the carbon where leaving group is present. So because of the poor overlap between these two adjacent sp2 hybrid orbitals, the triple bond is a very weak triple bond, and this can be easily attacked by the nucleophile, and this can lead to the formation of different types of products. Now if we explain the mechanism of this involvement of benzene intermediate, this can be explained based on two steps. First step is the elimination step. So what happens is, this amide ion abstracts the ortho hydrogen present on the aromatic halogen compound. So for this chlorobenzene, this hydrogen or this hydrogen, they are equivalent hydrogens. So either this hydrogen is removed or this hydrogen is removed, you will get a symmetrical type of intermediate. So in the first step, amide ion will abstract this proton, and this proton will be eliminated with the formation of a triple bond, and this type of benzene will be formed as an intermediate, where this carbon is C14 carbon and this carbon is C12 carbon. Then the liquid ammonia present can attack either this carbon C14 carbon, or this can attack C12 carbon in the second step, which is called as addition step. because this nucleophile is going to be added either at this carbon or at this carbon. So if path A is there, that means this ammonia has got attached to C14 carbon, we will get this type of intermediate, where this negative charge present on the adjacent carbon will abstract this proton, and we will get this type of product in 50% amount. Similarly, if path B is involved, then ammonia will attack as a nucleophile at the carbon adjacent to the C14 carbon, and we will get product B. So this is how we get 50% of these two products, and this explain the existence of benzynes as intermediate in these types of reactions. Then further evidence for the existence of benzene was done through trapping experiments in case of reaction with different types of nucleophiles or dienes in D-Elder reactions. This acted as a dienophile. So this dienophile can react with this diene furane, and we will get dihydro epoxynaphthalene as the product after trapping experiment. Similarly, these two molecules of benzene, they can dimerize to give us biphenylene as the product. Then this can undergo Diels-Alder reaction with anthracene, where this is acting as diene and this will act as dienophile, and we will get tryptosine as the product. Similarly, this can benzene can react with substituted 1,3-butadienes, and we can get these types of product, dihydro 1,4-dimethyl naphthalenes as the product. So when all these reactions were done, these products were actually isolated, and based on these trapping experiment, it was established that this type of intermediate is involved in benzene mechanism, and this type of reaction is an example of elimination addition mechanism for nucleophilic aromatic substitution. And with further experiments, benzene was trapped at 6K in frozen argon, and the values for the triple bond was found to be 1.26 angstrom units, which is longer and weaker than that of ethyne, because in ethyne it is 1.20 angstrom units, whereas this adjacent carbon-carbon bond is 1.39 angstrom units, which is slightly shorter than that in case of benzene. So the bond length was also discovered in case of benzene. Then some mechanistic product formation in benzene mechanism. So as you know that if there is some electron withdrawing group is present at any of the carbon of benzene, then because of the electron withdrawing nature of this group, this will stabilize the negative charge. So closer the negative charge, better will be the stability of that benzene, and because of this addition of nucleophile to the benzenes having electron withdrawing group will take place in such a way that negative charge should be closer to the electron withdrawing group. So that product will be formed in more amount, or that product will be favored where the addition of the nucleophile will lead to the formation of intermediate where negative charge is closer to an electron withdrawing substituent. So for example, if in this case the ammonia as a nucleophile attacks either this carbon or this carbon, so if the ammonia attacks this carbon, that means this carbon is meta with respect to this electron withdrawing group, we will say meta attack, and this carbon is ortho with respect to this electron withdrawing group, we say ortho attack. So if ortho attack take place, that means the NH2 group will get attached to this position and this will acquire the negative charge. Whereas if ammonia gets attached to meta position, then negative charge will be present at this carbon. And if we compare the closeness of the negative charge with this electron withdrawing group, the negative charge is more closer to electron withdrawing group in this intermediate. So the meta attack in such type of intermediates, that will be favored because here the negative charge is closer to the electron withdrawing group, and ortho attack will be disfavored because this is away from the electron withdrawing group. Similarly, if the triple bond is present between meta and para carbon, then attack can either take place at meta position or it can take place at para position. So here similarly, if attack takes place at meta position, then negative charge will be present at this carbon. If attack takes place at para position, then negative charge will be at this position. If it takes place at meta position, then negative charge will be at this place, and you can see clearly in this case the negative charge is more closer to electron withdrawing group. So that is why this intermediate will be favored in place of this intermediate. So more of the product will be formed via this attack, less of the product will be formed via this attack. Similarly, more of the product will be formed via this attack, less of the product will be formed at this attack. So this is how the presence of substitutions affect the formation of products in different types of unsymmetrical benzynes. Then when a substituent is present in aryl halide in an unsymmetrical arine, as you have seen in the previous slide, for example, if this is the case, then we will get this type of benzyne, and here now we are having the electron leasing group attached to the benzene ring. So here either ortho attack can take place or meta attack can take place, and this can lead to formation of product either through ortho attack or through meta attack. So we will get two products in such cases, and in case of electron leasing groups, most of the product formation is 50-50. Then if we are having this type of toluene, chlorotoluene, para-chlorotoluene, then the benzyne formed will be this one. Attack can either take place at meta position or at para position, and both the products, they will be formed either from para attack or from meta attack, but they will be formed in 50-50 ratio. Then when we are having ortho substituted, as I have told you that two products, they are formed in 50-50 ratio. But if I replace this methyl group either by trifluoromethane or by methoxy, then the product formation is affected. And if you see this one, because of the presence of this electron withdrawing group, if meta attack take place, that means negative charge will be at this position, more closer to this, and only this product is formed in this case. No product is formed where the attack of the nucleophile take place at the ortho position because of the high electronegativity of these fluorine atoms, this group is very greatly electron withdrawing in nature, and because of that the attack of the nucleophile is not taking place at ortho position, but it is taking place at the meta position only. And surprisingly, in case of methoxy also the same thing happens. The product is formed only from the meta attack, which shows that the electron releasing ability of this two lone pair present on oxygen is not taking place in case of these benzynes. Only the electron withdrawing effect of methoxy because of the electronegativity difference between carbon and oxygen, this is withdrawing electron density towards this, so that concept is taking place, and because of that only meta product is being formed. Thank you very much. So these are the references which has been included in this lecture, and this is the link for the other lecture, that is SNAR mechanism. Thank you very much.